Yeah, I'm glad to be here. So I think this is a nice follow-up sort of from the previous logic colloquium where they talked about computability and density and intrinsic density and how difficult are problems to solve. So I thought it would be kind of interesting thing to bring in logic from the perspective of program verification. So I am a person who works in formal methods and formal verification. So essentially what I do is you give me mathematical description of a system, you give me a property, and I develop algorithms for checking whether the system satisfies the property. And logic is one of the, if not the most powerful tool that we use often. There are many logics which are inspired from philosophy, like temporal logics, which have made great efforts in computer science, and they have been awarded. They have been given Turing awards. And one thing is that this area of verification and using logic has one disproportionate number of Turing awards in computer science. So. Okay, anyway, with that I want to start. I mean, it's a bit of a stretch, but I'm trying to define, give a definition of logic, and this is what it says in the Oxford English Dictionary. It's kind of naive, so that a bunch of logicians meeting together, and I'm giving the definition of logic. Anyway, so the way I want to see logic is that it is a tool for pursuing truth. As in, if you want to find out what is true, then logic is more or less your only source. In some sense, logic, that's it. So let us start with the simplest of the logics, right? So the simplest logic is propositional logic, where you have propositions which are either true or false, and you have Boolean combinations, you have an and, you have or, you have implication, you have equivalence, etc., etc. I mean, you have truth tables, logical entailment, etc., right? So the reason why I'm introducing this is that there's a point. I'll get into it later, but if you have, I mean, in propositional logic, you have what we call as a proof system, as in a set of rules which you can use to infer truth. Right? So here in one slide I'm presenting the logic or the proof rules in natural deduction. So natural deduction is one way to infer a given property from a given set of formulas. That is, if you have a formula phi to be true and if you have formula psi to be true, you can infer phi and psi to be true. Similarly, if you have, if you assume phi and if you can infer psi using one or more of these rules, then you can infer phi implies psi to be true. This list goes on and on. There is not the only way for inferring truth in propositional logic. There are other ways. There have been equivalences, etc. Right? An example proof. I'm just illustrating it with an example. Here we have an assumption that is, if I'm given Q implies R, then can I infer P or Q implies P or R? And you can use one or more of the rules that I showed above in the natural deduction framework, and you can essentially infer the truth or truthfulness of the given proposition. So here we assume Q implies R. In the first step, it is given as a premise, and then we add assumptions, etc., etc., and then we infer Q or R implies P or R. Right? So what does this proof essentially mean? One way or one perspective of looking at it, which I will try to extend it to other domains, is that this proof essentially assigns a meaning to the propositional formula. That is, if you assume if you assign the assumptions to be true, then the meaning that you can assign using this proof is that the consequence is true. So, what would happen if you have more complicated formulas? Then, well, you would go to more complex logic, right? So, here you have predicate logic, where instead of just having propositional variables, you have domains, and you have terms, you have functions, you have predicates, and of course, there's first order logic where I have predicates over, essentially over existential quantification over variables. I don't have existential quantification over predicates, but I can encode many interesting properties such as Fermat's last theorem using simple statements in predicate logic, right, in the domain of integers. And similar to predicate logic, I can similar to propositional logic, I can give proof rules. Well, these proof rules are a bit different from propositional logic because the truth that you assign for each of these consequences would be true in all models. But anyway, so essentially, my point is, in propositional logic, you have some proof rules which you can which you use to construct proofs, and these proofs assign meanings to this propositional logic. Similarly, you can use something similar in predicate logic to construct proofs which you can use to assign meanings to statements in the predicate logic. But what about more complex objects like programs, right? By the way, I want to tell that if you have any questions, feel free to stop me and ask me any questions. So, what about objects like programs, right? So, what does if I give you a particular program, what does a program mean? I mean, abstractly, I know it is a Turing machine, but what does it mean? As in, it's just a machine that keeps doing computation. Yeah, but we want to somehow reason about a program, right? In that sense, we want to turn to logic and find out, can we develop interesting logical frameworks where we can assign some truthfulness or assign some meanings to a particular program. So let us take this particular example, right? This particular program, although you can kind of think of it as a Turing machine, that is, it has a Turing machine where you give as an input an integer I on the first step, it does something, but the mapping of this to a Turing machine is not that straightforward, right? So you have these variables, I'm assigning them to j equals to 0 and k equals to 0, and I'm doing some loop, okay, and then I'm returning something, so you can think that I'm writing that on a final date. In this case, in a simple program like this, if I give an integer I, which is a negative integer, I have to kind of fix an encoding of the integers that I give as an input tape, and then the point is, this simple 9-line program, to just think about it in an abstract sense as a Turing machine, it requires a lot of heavy lifting. So we want to kind of, to assign meaning to a particular program, it's not too useful to have or to look at the abstraction of a Turing machine and say, like, yeah, each state has this, it reads a particular tape alphabet and it moves to the next state. It's not that convenient, rather, let me put it that way. So, but if you want to look at programs as themselves, they are fairly ridiculous. And to keep it in a BuzzFeed way, programs are not always well defined, right? If I give a particular input argument and if I have a division by that, how do I define that? And another thing is, this program may not terminate. And the worst thing is that because these problems are undecidable, there is no algorithmic way to tell if something is well defined or whether something terminates or not. So we are kind of stuck with a very, very different problem. It's just that programs are useful in our day-to-day lives and we want to reason about them, but thinking of them in terms of Turing machines are not useful. They have several problems. They are not always mathematically well-defined objects. So in this talk, what I'm going to present to you is my understanding or the way I see one way to define what a program is. So in this talk, I'll talk about Hoare logic, which gives one particular semantics of programs. There are other semantics as well, and all these semantics have been proven to be equivalent. This entire thing was done in around the time of 60s and 70s, and the people who started the Hoare logic, both of them won Turing Awards. The people who proved equivalence of Hoare logic with other semantics of programs, even they won Turing Awards. So it's like there are Turing Awards floating around this world. I will introduce Hoare logic, and I'll try to define what do I mean by a program, and just thinking of programs in terms of programs and not getting boggled down with the details or abstract notion of Turing machines. And I mean, we know that in propositional logic, we know that it is sound and complete. That is, whatever is true can be inferred. Whatever you infer is true. So similarly, there are some theoretical guarantees that you can give for Hoare logic. Not all of them, of course. And I want to try to tell you that it's not all in theory. This is kind of a practical, I mean, it is fairly practical. I'll try to give you a few demos. I think I have 2 examples which I use in my graduate class. I'll try to convince you that this does work in many instances. I mean, of course, all bets are off, and I'll explain what I mean by all bets are off. And I'll finally give some tools, and I'll also discuss what are the problems with the logic that I just discussed. Okay, so before we talk about programs, let us define the syntax of a program, right? So for this discussion, I don't want to complicate a lot of things. So let us assume that we just have integers, and we have some fairly defined constants. So we have expressions. So first is we have variables, which I'm assuming are integers. And then I can have expressions which are either integer constants or variables or arithmetic operations on these integers. And I have Boolean expressions which are comparisons on these integers. And then a program is essentially a syntax where I have 4 statements, right? So first is an assignment statement, that is, I compute an expression, and whatever value that expression has, I'll assign it to a variable. That is, at each and every given point of time, I have a given expression has a value, and I'm assigning that value to an expression to a particular variable. Or I can have sequence of such assignments, which is C semicolon C, that says that I have one statement, after that I have another statement. And then I have this if then else construct, which says that I'll evaluate this Boolean operation, and if this is true, then I'll operate the first statement or first set of statements. If this is false, I'll operate the second set of statements. And then finally the while construct, which says that as long as this proposition B is true, keep evaluating the C the set of statements C, right? So essentially, you can think of a program as a sequence of one or more of these statements which supposedly accomplish a given task. The reason why I say supposedly is because, well, we have to prove that that particular program accomplishes the task that we want. And what I'm trying to give you is essentially how do we infer even such inferring, but whether a given program accomplishes a task is not a trivial problem, right? So say that I'm given a program, and what do I mean and how to prove what do I mean by a program, and how do I prove a program to be correct? So this particular framework that I'm going to talk about, which is called Hoare logic, is developed by Tony Hoare and Robert Floyd. They developed it around 65, around that time. And so essentially, their idea is the following. A program by itself is just syntax, right? There is nothing more to a program than just a sequence of characters. But mathematically, what a program does is that it takes a particular state, that is, I assign a particular valuation to each of these variables. Each statement in the program changes the state of in the sense that each statement changes the state of the program, and by a state I mean that at a given point of time what are the values that correspond to each of these variables. And if a particular program terminates, or if a particular program executes a sequence of steps, and if it terminates eventually, then it ends at a final state, and that's what a program is. And we say that it is correct if the final state, or wherever we end up with, satisfy the predicate that you want it to satisfy. So to put it concretely, say I have a C program, it starts with the main code, and at the beginning I have a given state, right? So at the beginning I have a state where I assign 0 to all integer variables, and I want to do some computation. Say I want to compute n factorial or sum of numbers up to n or something like that. Then whatever is at the end, the state that's at the end, that should satisfy some correctness predicate, and that is the intuition of it. Okay? How do I go about doing it? And the way the proposed framework, how they do it is that they introduce what we call as triples. So a triple is a set of three things. In this case, a set of P, C, and Q, where P is the precondition, C is the statement, and Q is called the postcondition. So what do I mean by this triple PCQ? So for a given statement or a set of statements C, if at the beginning or before C the precondition P is satisfied, then after C the postcondition Q is satisfied. So that's the main idea of a Hoare triple. As in, I have a precondition, then I run this particular program, and if this terminates and ends up at a final state, then I have a postcondition Q, and that particular Q is another predicate which is satisfied by the state whichever arrives after executing C. Right? Any questions so far? Okay. So what are some examples? Although I'm kind of taking a liberty of writing the square root function, keeping that aside, so one particular precondition postcondition here is that I have x equals to square root of x. The precondition says x greater than 2, and the postcondition says x greater than 1. Right? Well, you may be wondering that x greater than 2, well, the square root of x is 1.414 something. So x greater than 1 is true, but x greater than 1.1 is also true. Right? I don't care. As long as the postcondition Q is satisfied, in this case, I don't care if there are other states or if there are other predicates that also satisfy the postcondition, although I'll talk about that a bit later. But essentially, starting from a given precondition, if after the termination the postcondition is satisfied, then that's a valid Hoare triple. Right? And here I have another example where x is less than minus 5 and y is greater than 0, x equals to x plus y, x less than minus 5 and y greater than minus 5. Right? So, okay. Essentially what this means is the fundamental point that I want to get across is that this particular way of defining Hoare triples assigns a meaning to a program, or it assigns a particular meaning to a particular statement. What it says is the meaning of a particular statement is that all the set of Hoare triples it can satisfy.
So we've had a sort of precise language for the expressions. What predicates are allowed?
Any predicates, as in, yeah.
Okay, so it's just sort of anything at all that we can say.
Yeah. So yeah,
Yeah.
anything that everything that you can say. Although in this particular talk, I will restrict to probably first order logic. That's it. Yeah.
But in general, you just sort of allow any old predicates in there.
Yeah. I mean, as long as So the predicate should be well defined so that if you give a particular state, the predicate should either be satisfied or not satisfied by the state. And similar with the precondition, and similarly with the postcondition. So, okay, so this is the Hoare logic proof system. So what this says is, if I can have different pre and post conditions for each of the statements, how can I put them together to infer pre and post conditions of more complicated statements? So there are 5 rules, because, well, we restricted our attention to very simple programs where we have assignments, sequential composition, if then else, while, and the final one is fairly interesting. Okay, I don't want to. I'll discuss each of them one after the other. Okay? So, what does sequential composition do? So, sequential composition says that if you can somehow give me the pre and post condition of a set of statements C1, saying that phi C1n is a Hoare triple, and then if you can give me phi C1 eta is one Hoare triple, and if you can give me eta C2 psi as another Hoare triple, then because the precondition of C2 is same as the postcondition of C1, I can put these two things together and I can infer phi C1 sequential composition C2 psi. Okay? So notice that this makes intuitive sense, but this is a fundamental proof rule. So we know how a program should work. A program should take one sequence and it should apply these things in one after the other sequence. But you see that this is a logical rule, and this is how we want the programs to work. I mean, we can have a weird programming language where C2 is executed before C1, and you need to write the program in reverse, but that is completely counterintuitive. Right? So what this particular statement says is that it caters to our intuitive notion of programming, saying that it starts from the first statement and goes to the second statement. Right? So this is how we assign meaning to syntax that we have given to our programming language and assign it to the triples phi and psi. So I have one simple example here. So x greater than 2, you have statement x equals to x squared, then I have x greater than 4. And if x greater than 4, x equals to 2x plus 1, x greater than 9, then I can put these two things together because the post condition is the same. Right? If you take a look at the second example, the post condition I have is x greater than 4 here, and there it is x greater than 20. Sorry, you can't do anything. Why? Because this particular sequential composition requires that the post condition of C1 should be same as precondition of C2. Can we do anything more? Probably, but at least using this rule we cannot do anything. Right? So let me go on to other rule. This is if then else. So if you have this if then else statement, then what this means, or what the precondition and postcondition should satisfy, is that, so if the condition B is so assume that B is a predicate that is evaluated at a particular state. So if you have phi and B as a precondition for C1, and as a postcondition you get psi, similarly you have phi and negation of B as a precondition for C2, and as a postcondition you get psi, then I can put these two things together in an if-then else statement and get phi as a precondition to if B C1 else C2 and psi as a postcondition for that. Right? So that is, so this assigns a particular meaning to this if-then else statement. That's the main thing that I want to emphasize. So we can have an if-then else statement where if B is true, then evaluate C2 and then evaluate C1, but that is not the intuitive notion of programming we have. Right? So this, the beauty in this work is that it assigns a particular meaning for each of these constructs. So here, when we write an if-then else statement in our programming, what we want is if the condition is evaluated, then run C1. If the condition is false, then run C2. So similarly, if you have any question? Okay. So if you have so notice that the post condition of C1 and C2 should be the same here, right? And the precondition for C1 is that phi and B should be satisfied, and the precondition for C2 is phi and negation of B should be true. Right? So here I have one example. So here the precondition is x greater than or equal to 0, x less than 0, and then we can use these two. And notice that the post conditions are the same. We can use these two to evaluate the pre and post conditions of the if-then else statement. Right? Next, this is kind of an interesting rule. It's an implication. What this says is, if you have a pre and post condition, which is phi, a set of statements psi as a Hoare triple, and if you can generalize the phi as phi prime, and if you can specify the psi or if you can strengthen phi to phi prime, and if you can weaken psi to psi prime, that is, notice that here I have phi prime implies phi, which means that all the states that satisfy the predicate phi, all the states that satisfy phi are a subset of states that satisfy phi. Phi prime are a subset of states that satisfy phi, and all the states that satisfy psi are a subset of states that satisfy psi prime. Right? So if I have these three conditions, that is, if phi C psi and phi prime implies phi and psi implies psi prime, then I can infer phi prime C psi prime as another Hoare triple. Well, I mean, this makes it, so this is one of the proof rules that are given to us, that's it. This is kind of an interesting one. It's called a partial while for a reason, and the partial while says that if you give me a particular statement and give me a Hoare triple such that at the beginning of C, the precondition of C says that psi and this Boolean condition B, and at the post condition the predicate psi is true. Right? So an example of C would be that I have two variables x and y, and I increment x and I increment y. So after the end of this particular statement C, I increase both the values of x and y. So the value of x and y at the beginning are same as the value of x and y at the end. Right? So if I have such a Hoare triple, then the Hoare triple that I can infer for while BC is that the precondition is psi and the post condition is psi and negation of B. Right? So a question is, don't you find anything wrong with this? I mean, what if the loops are a big problem, right? What if the loop does not terminate? So, okay, let me go through this again. So I have, in this particular statement says that if I have psi and B as a precondition, if I run C, and I'll get psi as a postcondition. But this means that this particular statement might terminate. Assume that C terminates here, but this loop while B C may not terminate, right? So how can we write a pre and post conditions for that?
I mean, if you never reach a post state, then the post condition is sort of trivially doesn't even apply.
Okay. So that's the way they break this particular paradox. As in, what they say is that you can write these Hoare triples, and if the program terminates, then the post condition is true. I cannot say anything about whether the program terminates or not. If the program terminates, then whatever the post condition that I have, or say if this particular while BC loop terminates, then whatever state that is reached after that would satisfy the predicate psi and negation of B. If it doesn't, then I don't know.
I'm not sure if that works. Because what about the case where it terminates vacuously? So at the initial state, B is already false. I mean, yeah. In that case, we don't know from a premise that precondition psi and B gets you the output.
So you're saying that if a particular loop where B is vacuously false, that is fine, right? Because my post condition says psi and negation of B.
C will
but
never
we
be
did.
executed.
We didn't get. Because it's psi identically on both sides.
Yeah, it is psi identically on
Right,
both
because
sides.
that would be a problem if your seed were actually serving a function of converting from a non-vacuous precondition to something
Yes,
else.
it would have been a problem there. Yeah. Yeah.
So just to clarify, the partial in the name here, partial while, is because this rule can move us from a terminating program to a non-terminating program. Is that what's partial
Rather,
about it?
the explanation that they give is that this is a partial proof of correctness of a program, because the total correctness would mean that I know that the loop terminates, and whatever I reach at the end is the correct. That satisfies the correct predicate.
Okay, so
this
two
only
notions
gives
of correctness. Okay.
So this only is. I mean, I can give a particular. I can prove. I can give the Hoare triples for each and every part of the program, and even then, the program may not be completely correct because it may not terminate. So if it terminates, then whatever post condition is true, that whatever post condition I give is satisfied by the system, by the state. But so that's why it's only a partial proof. That's why it's called a partial while. I'll present a total while as well, where they just add one more thing to it, and it looks like a band-aid, but it seems to be working fine. So this is a total correctness for while, right? And the band-aid that they throw is that I have a function e such that it decreases. So it's the same thing. I have this precondition eta and b, and I have a predicate e which is greater than or equal to 0, and at the beginning of C it is assigned some value e0, and after C I have eta and e at the end is less than e0. So, and because I am assuming integers, and you have to decrease by at least 1 if you have a strict less than sign, that's why I have that. Well, this wouldn't work if e is a real valued function, clearly, right? So this kind. So here you need not just the. So here we give names to these things. So here eta is called the loop invariant, and e is called the ranking function, because it ranks how many times a particular loop has run. So you need to give both these things, and this is the total correctness, because now I know that the state whatever is that's at the end satisfies the predicate that is given in the postcondition, but I also now know that the program terminates. So that's the reason why this is called total correctness. So this is a very interesting one. So I kind of preserved this to the last, and this is called assignment. So if I have x equals to e, which is that there is this expression, and x is assigned whatever the expression satisfies, notice that there is no, I don't need anything upfront, as in it is derived from vacuously, as in I can derive this as a rule without having any premise. So what do I derive? If the postcondition for x equals to e is the predicate psi, then in the precondition it should be the case that if I replace the variable x with the expression e, the predicate psi should be true. So essentially, so let us take this particular example. I am assigning y equals to x plus 1, right? Y greater than or equal to 6 would mean that the precondition to that is here I replace y with x plus 1. So essentially I replace x plus 1 greater than or equal to 6, and the precondition is x greater than or equal to 5. So this is one of the most important rules, because you don't need any premise to infer this. So essentially the proof would look like I have these Hoare triples for each of the assignments, then I combine them together in if then else and loops, and then I give a loop invariant, and finally I get a total correctness proof of the entire program. Okay? So essentially what I want to,
Can I just ask one question, sorry, real quick about that rule?
Yeah.
So I assume sort of in the background you have some convention about not binding variables?
Yeah.
So X is not free and...
So in this particular program, we assume that all the variables are given unique identifiers. Let us say that because our program is static, we rename all of them and no two variables have the same name. That may not be possible in, say, if you take lambda calculus, but in this case, because you are talking about imperative programs, it is possible. So, as I've told you before, this particular logic assigns a meaning to a program, right? So, a meaning of a program is nothing but what Hoare triple can you prove of that program is all the Hoare triples that you can prove about the program are what the program means. So this particular way of interpreting a program is called axiomatic semantics. There are other semantics called operational semantics, denotational semantics, etc. And they all have been proven to be equivalent for, so all this work took place around the 70s and the 80s. Now, there are a few more derived rules which are more intuitive to understand. Let us focus just on the first statement. So, it's a pain to have the same phi and negation of p here. So, this is just a syntactic sugar for the other thing. So, here I have phi 1 c psi and I have phi 2 c psi and from that I can infer b implies phi 1 and negation of b implies phi 2. That as a precondition if b c1 l c2 psi. I mean, you can take this and it's more or less the same thing. So this versus the if statement, both these are essentially equivalent. It's just a different syntactic way of representing it. Similarly, you have this while here. Instead of having psi and b c psi while b c psi and negation of b, what people prefer to write is phi c psi, because they want to have some consistent notion that Hoare triple should have two different formulas at the beginning, should be able to have two different formulas at the beginning and the end. So here it requires, in this case, I'm talking about partial while. So here I have, I bring in something from from the implication rule as well, and I need that phi implies eta, eta and negation of b implies psi, and this is the partial rule. So with these three, I can infer this. So, well, the bad news is that Hoare logic is undecidable. Essentially, what this means is I cannot assign meanings to all programs, and that's purely a function of undecidability of theory of natural numbers. If you can give me a particular engine which can tell whether a given formula over natural numbers is true or false, then I can, because I cannot give any such machine, this particular, I cannot prove all properties of Hoare logic. But everything is not lost. So Hoare logic is sound, which means that whatever I derive using Hoare logic is correct. And it satisfies an interesting property called relatively complete. What does relative completeness mean? So suppose, for example, that there is an oracle which can tell me whatever, no matter which formula I throw at it, existentially quantified over natural numbers, it can give me whether the formula is satisfied or not. If you can give me such a particular oracle, then all the true properties of programs can be inferred by Hoare logic. So it's kind of like completeness over the propositional logic, where all true statements have a proof. Similar to that, here all correct programs have a proof modulo the fact that I have an engine which can prove, which can tell me whether a given formula over naturals is true or false. So that's the relative completeness. Well, is it practical? Do we use it in real life? The answer is both yes and no. I know that there are some industries where there are mathematicians using pencil and paper to prove or to come up with these Hoare triples and compose these Hoare triples and reason at least about the most critical part of safety critical software. I know of those instances, but it's not possible for the regular software, right? If you take MS Word, for example, it has 100 million lines of code. I don't know what they have in it, but if you want to spend, if you want to put enough effort to reason about that, good luck. It's not going to be possible. So it's not practical for large software. And also there are some other settings where it is not possible but are safety critical. So for example, I have a safety critical software, say something that is running our aircraft, and I want to avoid a very silly thing, which is I don't want to have any division by zero errors in that particular code. Right? You have these sensors which are taking information, you are doing all sorts of crazy computations, and I just want one simple property, which is division by zero error, to be avoided. Right? In that, if you try to give Hoare triples for each and every statement in a large code base, it's not going to work. But after this, there have been several proposed mechanisms which do handle such targeted towards these specific cases where buffer overflow errors or division by zero errors. And there are some successful techniques which are follow-up in the domain of program verification after Hoare logic, which do that. Any questions? So this is where I kind of stop talking about the logical part of it, and now I kind of go into the engineering part of it, as in what can we do and what is actually being done outside as of now. So, if you have talked to any of the programmers or developers, it's very difficult to get them to write code. Forget about giving them to give Hoare triples and proving the properties of code, right? So and most of the people don't even know about Hoare logic, or they don't study it in adequate detail so as to give these Hoare triples at for each and every statement in the program. So, well, what's the best you can do? You want to somehow mitigate the errors in software, right? So one kind of approach that many kind of companies or many developers agree upon is that, well, I cannot write the conditions for each and every statement, but I can put in some assumptions and I can put in some assertions. That is, if I'm implementing a function, I assume that whatever is given to me satisfies a particular criteria, and given that, at the end I can assert that these are some invariants that are satisfied. And now I don't care about what are the Hoare triples in between. Go figure, right? So in those settings, what we want to do is we want to infer these holes in the proof that we have, right? So we want to come up with these Hoare triples for each and every statement, and we want to piece them together to build a big proof, but we have these holes. And in this particular case, there are two strategies as to how to patch up these holes. And the guiding light for both these strategies is the implication rule, right? So I have this implication rule where I can either strengthen the precondition or weaken the postcondition, right? I can say that if a particular state at the end of a particular program satisfies a predicate psi, then it satisfies a bigger predicate psi prime. Or if you give me a predicate that satisfies phi prime, then it also satisfies phi. I can infer this more general. So given phi c psi, I can infer phi prime c psi prime, right? So what we want to do is to kind of figure out what are the weakest preconditions that I can come up with, or the strongest postconditions that I can give for each and every statement. So the reason why we want to give the weakest precondition is that we can further strengthen the precondition and still not lose any correctness. And the reason why we want to get the strongest postcondition is that we can weaken it and still not lose correctness. Right? I mean, of course, all bets are off because there is an undecidable problem. So we have that advantage saying that if you can't prove it, we can't prove it. Right?
Do you have in general that for a given postcondition there always is a weakest precondition, whether or not it's mechanically findable?
I will actually talk about it. Yeah. So let me exactly define what's a weakest precondition, strongest postcondition is. So if I'm given a set of statements C, and if I'm given a postcondition Q, weakest precondition of C and Q is a predicate P, such that for all predicates P where I can infer PCQ, P implies weakest precondition of C comma Q. Right? This is from the implication rule. Now there is again a problem with this, right? It's a statement in second order logic. I have given universal quantification over all predicates. Who on their right mind would generalize a statement from first order logic to a second order logic? But it turns out there's a good reason to do that. I'll tell you the reason why. Anyway, assuming that even after this illogical step of complicating the problem from first order logic to second order logic, how to infer this, right? So how to infer, if I'm given a Hoare triple PCQ, how to infer that? Well, to infer whether PCQ is provable, well, what we do is we have this magic function which computes weakest precondition of C comma Q and prove that P implies weakest precondition of C comma Q. Then we are done, right? And here is the reason why doing a weakest precondition is not so bad. The reason is I can come up with some sort of loosely an algorithm for computing the weakest precondition, right? So essentially, if I have two sequence of statements C1 and C2, and if I'm given the postcondition Q, then weakest precondition of C1 and C2 is nothing but I get the weakest precondition first with respect to Q of C2 and then with respect to C1. That will give me weakest precondition of both C1 and C2. Right? Similarly, if I have the assignment x equals to E, and if I'm given a postcondition Q, it is nothing but I take this postcondition, just replace x with the expression E. That's the weakest precondition. Similarly, if I have this weakest precondition, if I have this if then else statement, then I have that B implies weakest precondition of C1Q and negation B implies weakest precondition of C1 comma Q. So this sounds really promising, right? I can come up with an algorithm which can do everything unless I encounter loops. So if I have a loop, how do I compute the weakest precondition with respect to a postcondition? For computing the weakest precondition, I need the weakest precondition because it's a loop. And in the logic, I showed you need a particular psi and B, C, you have psi, only then you can infer any rule about the loop. Right, so this is where we we have a problem. So I'll talk about how to mitigate this problem later, but similar to that, we have a strongest postcondition, as in, so there are two strategies, right? I have in a program, say that I have some preconditions, I have some postconditions, and I want to infer all these four triples. I can do something similar, right? So I have strongest postcondition, which is that now I have the precondition P given, and for all Q such that PCQ is provable, strongest postcondition of C comma P implies Q. And I can give similar rules, but there is one thing that I want to point your attention to, right? So the sequential composition is somewhat straightforward. Assignment is somewhat interesting. So what does assignment, so given a precondition P, what's the postcondition of x equals to E? It says that there exists a particular x naught. So here I am adding n number of variables, which is the vector of all the program statements. There exists x naught such that x naught satisfies the predicate P, and x equals to this expression on, I replace all the values in x with the variables x naught. So essentially I am saying there exists x naught such that predicate P is true, and I am evaluating x as the expression that I am evaluating on x naught. Right? So this is a problem, right? Because now I have to, if I have to recursively compute it for several assignments, I am introducing new and new and new existential quantified variables, and it just gets worse. Right? So the if then else is somewhat similar, and loops, again we run into the same problem. For computing the strongest postcondition, we need the same. Yeah.
Just a thought though. Am I correct in thinking that the strongest postcondition following a loop guaranteed to not to halt would be false? Presume we have a true infinite loop.
No, probably no, because if you use the proof rule of partial while, it doesn't say anything about termination, right?
Precisely. So if the loop never terminates, then the postcondition never comes into play. We can simply put the statement false there.
Yeah. So if you know, yeah, exactly. So if you know that the loop doesn't terminate, then false is the strongest postcondition.
Right. So the question of whether the postcondition can evaluate false is equivalent on a loop is equivalent to asking whether it can halt.
Yeah. Yeah. So essentially, the question of loop termination is that is the strongest postcondition false for this particular loop?
Yes.
Yeah. That's very valid statement to say. So, okay. Let me talk more about the recursive conditions for loop. Okay? So the way we kind of deal with these loops is that we don't bother about the weakest precondition or strongest postconditions. one of the main challenges in program verification is to deal with loops, and there we always try to synthesize a loop invariant which gets our job done. That is, we want to calculate different loop invariants. I mean, a loop can have more than one loop invariants, of course, and what we want to do is essentially that we want to find a loop invariant and a ranking function, preferably a ranking function, which will be enough so that we can prove the rest of the pre and post weakest preconditions and the strongest postconditions that we have inferred. Right? So, okay, enough of this entire talk. Let me show you some examples and show you something very real. Is that visible? Probably not from the back. Okay.
The bigger issue is that it appears to be being cut off to the left.
No, that's okay. I don't think I would need yeah. So this is one of the elements from Microsoft Research. It's called VCC. You can try it online. The URL is riseforfun.com/VCC. And essentially this is something in production, and this is being used by developers inside Microsoft. And so what it would look like is that I have a program. I have to include this vcc.h, and I can assert different things in this particular program, right? So here I'm defining two integer variables x and y, and I'm asserting that x is greater than or equal to y, right? Well, when I just define two of them, this actually takes into account what the actual semantics of C, right? So when you assign two different integer variables, when you declare two integer variables, by default C does not have any semantics to it. In my case, I fixed that all of them are initialized to 0. In this case, it need not be the case, right? So you can try verifying it. So it says that x greater than or equal to y did not verify, right? Anyway, so this is very trivial example. They have much more complicated examples that you can start with. They can actually handle fairly complicated things. They can handle integer arrays. You can use quantifiers, or you can use for all quantifiers within programs. So this is quite a lot of engineering and science went into developing this particular tool. What I want to do is kind of show you some basic examples. So I'm writing a program where I essentially want to swap these two variables x and y. And the way I can infer that they are swapped is that I assign h to x and m to y, and here I am asserting that h equals to x and m equals to y. Now the swapping, I want to swap without using any third variable. And if you want to swap two variables without adding any third variable, it's a simple trick where you do x equals to x plus y, y equals to x minus y, and x equals to x minus y. So this is kind of, I mean, you can use a third variable, but what's the fun in that? So now, to prove, there are of course obvious problems with this, right? As in, if you use a 32-bit integer, and if you add two of them at the end point, you may go overflow, and so to prove that this thing exactly works, you need to add these assume statements. That is, assume x equals to greater than or equal to 0, assume x less than or equal to integer max, and then I have to add this additional statement, x plus y less than int max. So then it will infer, okay, now I just told that x plus y is less than int max, but what's the guarantee that x minus y is not minus 1 times int max? So it infers all those things automatically it has a background inference engine which learns all these intermediate Hoare triples, and then it pieces them together, and at the end I have assert this swapping, right? So h equals to y and m equals x, and then I can press this. Now the embarrassing wait, and then it says verification of main succeeded. So I'll give another kind of some simple example. So a simple example that I want to give is a loop where I add numbers from 1 to I. So it's a program that takes an integer I, and it requires I greater than or equal to 0. It requires I into I plus 1 less than int max, and then so here, because I have a loop, I need to specify this invariant. I need to give this invariant. So what it will do is that it will do two things. First is it will infer whether this particular thing is actually an invariant or not, and then it will try to come up with other intermediate steps in the whole logic so that I can prove the assertions that are given at the end, right? So here assert j equals to I, and assert k 2 times k equals to I into I plus 1, right? So essentially it says k equals to I into I minus 1 by 2, which is sum of integers until I minus 1. So this particular tool has been around for around 10 years, I think. But nowadays they are using, this is being used by actual developers in Microsoft, at least in some teams. Now everything is not done, right? I gave one particular way to prove programs, but notice that I left a lot of things aside, right? So real life programs are nothing like what I showed. Real life programs have side effects, that is, people want to do all these crazy optimizations, so they do if I plus plus greater than j minus minus plus 1, and they write all these kinds of side effect code where just to check the condition you will change the state of the system. So in this particular case, I did not talk about side effects at all. I did not talk about objects or classes, and that's an entirely different thing at all. Here I don't have any dynamic typing, right? I did not talk about arrays, I did not talk about any data structures for that matter. I did not talk about pointers. But this is actually a very good starting point, and there have been a lot of works following this, and one kind of work that is being used or being currently researched upon is this topic of separation logic, which tries to do something similar. They want to come up with proof rules similar to Hoare logic, where they can prove properties of data structures. So if you have a data structure, if you have a pointer, then they would want to infer something about a data structure. Say if you have a tree as a data structure, then they want to prove that this particular tree, or the code that you have implemented a tree, or whether you have implemented a sorted binary tree, whether you have implemented an almost complete binary tree, all those sorts of proofs that you can give over these complicated data structures. So this is one of the things that is currently being pursued. There are a lot more things that I did not talk about. So with that, I'll probably end my talk and I'll take any questions.